The second connection is a parallel connection. For these two ports, G parameters of the first two port is G prime, and of the second two port is G double prime. Connecting their inputs and outputs in parallel respectively, we get a new composite two-port network. Now we want to find the G parameters of the composite two-port. In this connection, U1 equals U1 prime and equals U1 double prime. Similarly, U2 equals U2 prime and equals U2 double prime because the input ports and the output ports are all in parallel connection. For the current relations, I1 equals I1 prime plus I1 double prime, and I2 equals I2 prime plus I2 double prime. So I1, I2 equal G prime times U1, U2 prime, U1 prime, U2 prime plus G double prime times U1 double prime, U2 double prime. Because U1 equals U1 prime equals U1 double prime, and U2 equals U2 prime equals U2 double prime, it equals G prime plus G double prime times U1, U2. The G parameters of the new composite two-port is G prime plus G double prime. The G parameters of the parallel two-port networks should satisfy this relationship. One point should be emphasized. When the two-port networks connected in parallel, their port conditions are possibly broken, then the above relationship between their G parameters will be false. In other words, the G parameters of the composite two-port isn't equal to the sum of the G parameters of the two parallel two ports any longer. Look at a simple example. This is the first two-port network, and this is the second two-port network. Connect their inputs and outputs in parallel to get a composite two-port network. The port voltages are still 10 volts and 5 volts. Let's analyze the voltage-current relationships of the branches before and after the parallel connection, and examine whether their port conditions are broken after the parallel connection. Before the parallel connection, the current of this branch is 1 ampere. The voltage across 2.5 ohm is 5 volts, so the current is 2 ampere. The voltage across 5 ohm is 10 volts minus 5 volts equals 5 volts, so the current is 1 ampere. So the port current is 2 amperes. According to the port condition, the current of this branch should be 2 current before connection. By applying KCL to this node, we get that the current here is 1 ampere. Let's focus on the two-port network below. The voltages are 10 volts and 5 volts. Because the currents flowing through these two resistors are same, their currents are 1 ampere and 1 ampere respectively. The current here is 1 ampere, and the current here is 1 ampere too. Therefore, before the parallel connection, all port conditions are satisfied. What's the variance of the port currents after the parallel connection? For this two-port network, the port voltages are unchanged, so the currents of each branch are still 1 ampere, 1 ampere, and 2 amperes. Here is 1 ampere and here's 2 amperes. But is the current here still 2 amperes? We can see the 2.5 ohm resistor is short by this line after the parallel connection. In other words, this is a short circuit. So the current through this 2.5 ohms resistor is 2 ampere, not 1 ampere any longer. Correspondingly, the current here is 2 amperes. Obviously, the current through this 2.5 ohm resistor is 0. Or this branch will have voltage drop violating the KVL. The current here is 0, and the current here is 0 too. The composite port should still satisfy the KCL. So the current through this branch is 4 amperes, not 2 amperes any longer. Similarly, since the current here is 0, the current flowing out of here is 2 amperes, and the current flowing into here is 1 ampere. So the current flowing out here is minus 1 ampere, not 1 ampere any longer. Now you will find that after the parallel connection, the port condition of the first two-port network will not be satisfied any longer. The current flowing in isn't equal to the current flowing out at this port, so to this port. For the second two-port network, the port condition will not be satisfied any longer either. So after the parallel connection, these two networks are not two-port networks any longer. Certainly, the relationship between the composite two-port network and the original two-port networks that G equals G prime plus G double prime don't exist any longer. You may find out the G parameters of the new composite two-port network after class and examine whether the relationship of the G parameters of it and the original two ports still exist. The answer is no. In what case the port conditions won't be broken after the parallel connection? There is a special case. If both two-port networks have the common terminals, respectively, that is, they are transformed from the three-terminal network, then connecting their common terminals together in the parallel connection will not break their port conditions. For these two ports, each two-port has a common terminal. Connect their common terminals together and connect the other terminals together. This parallel connection will ensure their port conditions not to be broken, because the parallel connection of these two short circuit branches will not change the current topology. This connection is called the standard parallel connection. If you want to find the G parameters of a composite two-port network by connecting two ports in parallel later, you should check whether the parallel connection will break their port conditions.